Hi, this is Armand, and this is my EEC 10 final project for spring quarter 2017. It is a sound localization system that involves stereo recording, time delay recording, and audio band filtering. Now, before we see the hardware, we're going to start off with the block diagram of my LabVIEW VI, which begins with a time delay structure that is controlled by a Boolean switch, which is located here on the front panel. And if someone wants to use that time delay, they can use this control on the front panel to say how many seconds they want to delay recording from when they start running the program. And if they don't want to do that, then that's okay, because the rest of the program will still run exactly as if it weren't there. So I want to get to the main structure. Inside of there, you're going to start off with a file dialog VI that will pretty much let you customize your audio file however you want. I like this a lot more than what a lot of people are doing, which was a temporary file. Pretty much you can make your default file name, what type of file. So if you want to do MP3, if you're recording music with the system, you can do that. And then it'll start writing audio file, and this is your sample rate. And down here is the serial port options. Opens up the serial port that you can control through LabVIEW. And all of these options are controllable here, but luckily the defaults that we got from the example VI also are the same for the board that we're using, so that's not a problem. And then once you move into the while loop, the main while loop, you're going to start off with the DAC assistant that pretty much reads in the analog voltages coming from the audio in port on the MyDAC, and that's coming from the dual microphone circuit, and it's taking 20,000 samples at a 44.1 kilohertz rate. And then this is also, the whole thing is controlled by a Boolean switch located here on the front panel. And so after that, after the DAC assistant, the signal will go out, and first it'll take a combined signal of both the left and right waveforms and put it here on the front panel before passing through 3 filters: a low pass filter, a band pass filter, and a high pass filter, with the low pass filter being cut off at 400 hertz, and we're going to just call that bass here on the front panel, and that's controllable however much you want to control the bass. It's kind of like an audio equalizer. And then the mid-tone bandpass filter has a low cutoff of 450 hertz and a high cutoff of 2500 hertz. And then the high pass or treble is a low cutoff frequency of 3000 hertz and a high cutoff frequency of 10,000 hertz. So that's just one way that it filters out audio and will record whatever frequencies you want it to. And then the whole addition of these signals gets multiplied by a scalar of this volume. And then we split up that signal to left and right. And luckily my microphones were pretty in sync, and I didn't have to multiply either of the channels by a scalar to make them equal each other. So, but the option's there if somebody else would want to do that. And then we get a combined filtered signal waveform that goes here. And then also, if you didn't see, I have the left and right filtered waveforms by themselves here, and then pretty much their sum would be here on the combined signal. And then the data from this combined filtered signal is what gets put into this file writing thing here. The next part of the VI deals with finding the angle to read to the servo motor that is attached to the microcontroller, but we're controlling that serial port in this VI. So the way I went about it was, so you get your left and right filtered signals, and these are both called dynamic data, and you basically convert them to a single waveform, and you take the waveforms and the information from it and you build an array out of it. And I found the difference of the left and right maximum indices of these arrays, and this is what helps you find a time delay for how long it takes for sound to get from one mic to the other, because they're on the other side of the board, and when you make a sound on one side, it's going to hit the mic on that side first before it hits the mic on the other side. And for my microphones and my setup, this difference was usually either negative 14 or 14. It never went higher than that. And so what I did was I made a case structure that first tested. What I also did was I found the maximum values, which is basically the amplitudes for the waveforms that are getting turned into arrays. And I found the difference of those two and took the absolute value of that. And I said if it was greater than 0.5, which is what I kind of tested to found to be a good threshold for where sound wasn't just background noise and somebody was actually trying to make a sound. So if it's actual intentional loud noise, then first it's going to test if this array index is greater than 14, greater than or equal to 14, because if it's outside of that range from negative 14 to 14, then we don't consider it. So hopefully it should be less than 14. And then it goes to the second case, which tests if it's greater than negative 14, so we don't want it to be less than negative 14. And then once you get in here is where kind of the formula I had to come up with was that, so if you take 90 and you divide it by 14, you get 6.4, I believe. So 14 times 6 is never going to be greater than 90. And we want our servo motor angle being passed to it to be between 0 and 180. So whether you add or subtract 14 times 6, it's never going to be out of range. So I had a scalar multiple of 6 to multiply by that index if it's within the range of negative 14 to 14. And then I would add this to 90, which is the neutral position, kind of down the middle on the servo motor. So it would rotate to that angle. And since the integer, I had to convert it to a decimal string. And then this string, I just left indicator so that I would see it here. And that string gets written to the serial port. And then the serial port will close, and I'll check for error. And it will just keep running like that until you stop it. And that's pretty much how the VI works. Okay, so now that we've seen how the VI works, let's see everything work in action. So we're going to run it. It opens up our file dialog. I'm just going to call this project.wave. And we see it starts recording. And now to test the servo motor, we're out here. Oops. So as you can see, the servo motor rotates towards where the sound's coming from, and the waveform graph's obviously responding if I talk loud, then it's gonna get really loud. And so all in all, great success.